Hello guys, new day, new video. Listen carefully to these two statements. Number 1, an electron is a wave. Number 2, electron is a particle. What do you think which one is correct? I'll give you 5 seconds. Some of you might say number 1 is correct and some of you might say number 2. But what if I tell you that both are correct? You might think I have gone mad. But no, this is the truth. Today, we are going to learn 5 such strange phenomena of our quantum world. After hearing them, you will question your existence. So without any delay, welcome to the world of the quantum realm, which is stranger than fiction. Let us start with the first problem, wave-particle duality. After hearing the name, you might have some idea what this is all about. Wave-particle duality is a fundamental concept in quantum mechanics. It proposes that all particles, for example, light, electrons, protons, etc., exhibit both wave-like and particle-like properties. Or, in simple words, an electron shows both wave and particle-like properties. The concept was introduced by scientist Louis de Broglie in 1924. He proposed that all matter, including light and electrons, can behave like waves. His equation for his hypothesis, lambda is equal to h by p, shows how the wave-like behavior of a particle is related to its momentum. Later, the photoelectric effect, where electricity is generated when light hits a surface. This was explained by Albert Einstein, which proved the particle nature, and the Davison-Germer and G.P. Thomson's electron diffraction experiment proved the wave nature. But the most compelling evidence came from Young's double-slit experiment, which demonstrated the wave-particle duality. In this experiment, particles are fired at a barrier with 2 slits, and we observe a classic wave-like interference pattern on a screen behind the barrier. Interestingly, this pattern appears even when a single particle is fired towards the double slit. This raises the question, did the particle split and pass through both slits simultaneously? However, if we attempt to measure which slit the particle passed through, the interference pattern disappears, indicating that the particle passed through one slit or the other, not both. To answer this question, we need to learn about the second phenomenon, the observer effect. Sounds strange, right? Actually, it is stranger than fiction. There is much debate regarding the observer effect, but let's not go into that. So what does the observer effect state? That by observing something, one can unintentionally change it. For example, if we try to check tire pressure, some of the air will come out, although it is not that prominent in the macro world but creates a huge impact in the quantum world. According to the observer effect, when we try to observe or try to measure a particle, its wave function collapses. But here, observer is not always human. It can be any device or instrument for measurements. Remember the previous question? How when we tried to measure that particle, but simply we were unable to do so? But what is the reason? The reason is the observer effect. When we try to observe the particle, it collapses the wave function. So now there's another question bubbling in your mind. Why does observing collapse the wave function? So many questions. To answer this, we have to move on to our next topic, quantum superimposition. Quantum superposition is a fundamental principle of quantum mechanics. It states that a quantum system can exist in multiple states simultaneously. It was introduced and explained by the famous scientist Schrödinger. In quantum superimposition, a particle can be in 2 states at the same time. Or in simple words, just imagine a girl proposing to you. You are happy, but as a miser, when she went shopping, you became sad seeing the bills, so now you are happy and sad at the same time. Let's come back to the topic. According to quantum mechanics, that particle is in the superimposition state of a wave and a particle. So when we observe, we force the system to choose any one of the states, causing superimposition to collapse. But that's not it. He also proposed a paradoxical scenario, popularly known as Schrödinger's cat. A cat is placed in a sealed box with a radioactive atom that has a 50% chance of decaying within a certain time period. If the atom decays, it triggers a mechanism that releases poison, leading to the death of the cat. However, until the box is opened and observed according to quantum mechanics, the cat is considered to be both alive and dead simultaneously, existing in a superposition of states. So now, why does the observer effect collapse the wave function? This idea was used by Schrödinger to highlight what he saw as a problem with the Copenhagen interpretation of quantum mechanics, which suggests that particles exist in all possible states until observed, at which point they collapse into one definite state, according to quantum mechanics. That particle is in the superimposition state of a wave and a particle. So when we observe, we force the system to choose any one of the states causing superimposition to collapse. But remember, these are just one of many theories. There have been many theories explaining the observer effect, but this provides one of the most compelling explanations, and that discussion is for another video. For now, by breaking the chain, let's move on to our next topic, uncertainty principle. Another confusing term. From here, you will be even more confused. So what is the uncertainty principle? Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics, proposed by Werner Heisenberg in 1927. The uncertainty principle states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as its position and momentum, can be simultaneously known. In other words, the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. Or in simple terms, if you know that particle's position, you can't know its momentum and vice versa. Didn't understand? Let me explain how my teacher explained. Suppose you have a fan in front of you. When it is off, you can clearly see the fan blades and know the position of the blades. Now, when you turn the fan on and it starts spinning fast, it becomes harder to see the individual blades. They become a blur, and you can't tell exactly where each blade is at a given moment. But you do know they're moving fast. So if we know exactly where a particle is, we can't tell how fast it's moving. And if we know how fast it's moving, we can't tell exactly where it is. It's a bit like the fan blades becoming a blur when they spin fast. Well, we have reached our last topic, quantum entanglement. This is another magical phenomenon that happens in the quantum world. Quantum entanglement is the phenomenon of a group of particles. This occurs when particles are created together, interact with each other, or are close to each other. They become entangled in such a way that we are unable to describe the state of that particle without considering the other particle. Even if you separate those two particles to a very large distance, they will remain entangled. Or you can think of relations like twins or a best friend with the same vibe. No matter how much distance they are, they will always be related. Sounds very confusing, right? But wait, we are still not finished. Suppose we have two coins and they are entangled to each other. Now if I take one coin to the opposite end of the universe and toss it, suppose I got heads. So now according to quantum entanglement, the other coin must have tails. Hey, did you notice? It seems to violate the theory of relativity. Information is traveling faster than light. Does it violate? Subscribe for the answer. That's it for today, guys. I think this is enough for today. The part of quantum entanglement is too weird. Even Einstein said spooky action at a distance. Even I don't understand many things. But this was mainly an informative video, not an explanation one. So for an explanation, it will be another video someday. Well, see you in another video. Stay safe and goodbye.